There's no doubt that deep neural network is a hot topic in recent years. Nevertheless, as the capability of these neural network grew, so did their complexity. Due to the high storage requirement, a lot of network may not be as viable to be deployed in mobile devices and other low-level devices. Quantization of these network will solve the storage problem, since quantization could drastically reduce the size of the network without severely impacting the accuracy of the network. Thus, a good quantization method will allow the wide deployment of high-performance models in more low-level devices. Has the problem been solved before? Yes, many times actually. All these articles are just from our literature review, and there are many more articles out there. Our group proposed a novel quantization method that doesn't require retraining of the network and could thus be used to rapidly quantize existing models and potentially preserve or even improve the performance of the model. The datasets and models used in the project are datasets and models from Homework 1 Part 2 and Homework 2 Part 2. The MLP and CNN models could achieve above 80% accuracy in their respective classification tasks. Therefore, these two models serve as good baseline to evaluate the performance of our quantization methods. The general pipeline of our quantization method is as follows. Given a neural network model, we're going to extract weight and gradient parameters from the model. Then we're going to perform k-mean clustering with different loss functions on the extracted weights. In the end, we're going to remap all the weights of the model with their corresponding centroid found in k-mean clustering. Since the number of centroid, in other words, the amount of k, is a hyperparameter that could be tuned, our group experimented with multiple possible values of k. On top of that, we also experiment with two different k-mean clustering methods. The first k-mean clustering is the naive k-mean method that only takes the Euclidean distance of the weight and the centroid into account when performed clustering. The second k-mean clustering method is the core of our group's quantization method. With losses of the original network taken into account, it considers the partial derivative of loss with respect to weight and form a linear approximation of the impacts of replacing the weight with the centroid on the loss value of the model, and thus attempts to minimize the network's loss change while performing the clustering. By finding the argument of such distance metric, the new K-mean clustering will tend to minimize the network loss change while performing quantization. Thus, the second K-mean will be much more problem-specific than naive K-mean and will in principle provide a more stable and better quantization. Now let's look at the toy example to understand why the second K-mean method is superior. In this graph, the red line represents the relationship of the loss value with respect to weight number one, and the blue line represents the relation of the loss value with weight number two. The x-axis represent the weight value, while the y-axis represent the loss value. Assume that weight number one equals to 0 and weight number two equals to 5 in the network. Note that naive K-mean would automatically pick 2.5 as the centroid. If we replace both weight with this value, the loss of the network is going to increase by 3.75. Our K-mean method is going to pick 0 as as centroid, since absolute value inside our value function prevented the centroid from going to the negative value. This is going to increase the loss of the network by 2.5, which is a clear improvement from 3.75. Our evaluation metric is the accuracy of the network after quantization. Interestingly, the naive K-mean method completely failed on our MLP model. After remapping the weight to the centroid, the validation accuracy of the model dropped to near zero. Our group confirmed this result with ONNX quantization library, as the MLP model quantized by the library also performed extremely poorly. Our MLP model seems to be very sensitive to the parameter changes. On the other hand, our CNN model is very tolerant of quantization. Even naive K-mean is able to get very good performance. On the figure to the right, the x-axis represents the value of k, with 1 representing 2 to the power of 1, 2 representing 2 to the power of 2, and etc. We found that with naive K-mean, certain rest blocks within the network require more clustering in order to preserve the performance of the network. Nevertheless, naive K-mean still offers a very surprising and impressive result, with only needing 4 clusters for rest block 1, rest block 2, and rest block 3 in order to preserve most of the performance of the network. Nevertheless, even though our modified K-mean quantization's performance is not as good on the first 3 blocks, it is able to outperform naive K-mean drastically on rest block 4. This drastic improvement on rest block 4 is expected since rest block 4 is the block with skip connection and is therefore expected to be much harder to quantify. By taking the loss into consideration, the new K-mean method performed in this tougher task better as expected. The graph in this slide shown that our new k-mean quantization method definitely has its potential. If we're able to perform such layer-wise quantization for every single block of the CNN, we could effectively use a 4-bit index of a dictionary for weights instead of a 64-bit double precision floating point number, and thereby decreasing the size of the network by almost 16-fold.